guess there's something magical about it, the last day of class. Isn't that a sort of a magical sounding phrase? I think so. So we have the last day of class today. I want to, you'll see on the screen here, start by mopping up a little bit of chapter 7. Talk about an important theorem about Taylor series that we kind of ignored, even though it's actually very, very fundamental. Go ahead. I actually do want to continue Wednesday's lecture a little bit more for about 5 to 10 minutes. Talk a little bit more about what Cantor sets are, and talk about that very last thing I mentioned on Wednesday about a conjugacy. I don't know if you have to look at the notebook or not. And then we'll do our more general review, mostly spending our time in chapter 8, but then highlighting some things in earlier chapters. So what do we have to mop up in chapter 7? It's an important theorem here. It's this theorem. And I guess I am just in the closed book portion of the exam having you just state definitions of theorems from chapter 8. But if I had decided to expand it, probably this theorem would have been included as something you should be able to state. It's important enough for that. It says, suppose you've got a function that's infinitely differentiable, infinitely many derivatives on some open interval that contains the point C. Is that zoomed in enough to see it well? Okay. If there exists a positive number m, so that, okay, here's a similar notation that we used on Wednesday. I got parentheses around that n there. That means the nth derivative. When I didn't have parentheses around it on Wednesday, it meant the nth iterate, where you compose the function with itself n times, not a power. With parentheses, that's standard notation for the nth derivative. If the nth derivative is bounded by m, for all t and I and all n, which may not happen in many cases, but if it does, then the function not only has a Taylor series centered at C, but that they're equal. The function f and its Taylor series centered at C are equal for all x in the interval. That's a pretty big deal, right? I mean, we got our series for e to the x and cosine of x and sine of x, for example. They're constructed in such a way that all the derivatives match up at 0. Why does that make them equal for all x? Well, this theorem is enough to guarantee it. For example, you can use this theorem to show these facts. It's probably easiest to think about it in the case of the sine and the cosine, because in the sine and the cosine examples, those derivatives are always bounded by 1. All the derivatives. So it's pretty obvious in that case. With e to the x, the derivative is always e to the x, which is not bounded on the entire real number line, but is bounded on any finite bounded interval. I shouldn't say finite, I should say bounded. Any bounded interval, e to the x, and all its derivatives, which are also e to the x, will be bounded. And since you can apply it on any bounded interval to get equality, that's true over the entire real number line. You get equality over the entire real number line. It's not uniform convergence, but it is uniform convergence over any bounded subinterval for these examples. With other examples like 1 over 1 minus x, it's not uniform convergence over the entire interval of convergence, but over any compact subinterval, for example. Okay? So, just mentioning this for a few minutes, it is a big deal. Okay, and we didn't really spend time on it because I wanted to get to chapter 8. But it's a big deal, this thing right here. So what we've been doing so far with topology is sort of the basis of what is commonly called point set topology or axiomatic topology. But when you've heard that word topology before, if you have heard it before, you might have heard that it's related to geometry. Is it topology related to geometry? And I got a picture here that I found. You know, stuff like making cylinders, making Möbius strips, right? Twisting the strip of paper there, making other kinds of exotic objects. This thing's called the Klein bottle. Isn't that what topology is about? The answer is yes, partially. It's about that. The point set axiomatic topology is the foundation for a more geometric version of topology. So it's got its geometric aspects. It's also got its algebraic aspects. There's a subject called algebraic topology, where you actually apply group theory to studying topology. And our focus on topology has been more of an analytical bent. We've applied it to real analysis, and in particular, that generalization of the extreme value theorem, for example. So it's sort of got, you might say, three aspects to it: geometric, algebraic, and more real analysis type thing. But most people, when they hear the word topology, they think geometric. Another option for your foundations of math paper would be to, for example, delve into the more geometric aspects of topology. You can, for example, relate it to the Euler characteristic from discrete math. How does it go? The number of vertices minus the number of edges plus the number of faces for a graph, planar graph is always 2. You remember that, seeing that in discrete math? That's got geometric applications to surfaces, for example. That could be something you delve into in your foundations of math paper in January if you're interested. I do want to finish up a little bit more, like I said, with what we did last time. We were talking about chaos, the butterfly effect, especially focused on the logistic family of maps. You know, we made those graphs of the iterates, for example, over the interval. And we also talked about the symbol space, the shift map on the symbol space of zeros and ones. Each element was a sequence of zeros and ones. The question is, how do you relate those two things? I showed you some graphs that were supposed to hint at how to relate between the two. Let's see, where are they here? Let's see, I forgot to enter F sub u here. Ignore that graph. Oh no, okay. Well, I must have forgotten to enter something. Okay, let me just try to draw it on the board. We have a box like that, and the graph of the logistic map when mu is bigger than 4 looked like this, and it left the box. And then there was the graph of the iterates, the second iterate, the third iterate, the fourth iterate. For the function itself, those are the points that escaped the box after one iteration. We have also the graph of y equals x in here. So you got a c that starts in there, it's going to go out of the box and actually ultimately off to minus infinity if you keep iterating. The cobweb plots goes off down there. Those are the points that leave the box and leave the interval from 0 to 1 in one iteration of the function when mu is bigger than 4. The graph of the second iterate looks something like this, I think. It went above the box here and here, leading to two new intervals down here and here that consisted of points that leave the box, leave the interval from 0 to 1 under 2 iterations of f. And the graph, you can see it at the end of the last lecture, continued. I made the third iterate and the fourth iterate, and the Mathematica was supposed to indicate that there were more sets that you were taking out, consisting of points that leave after 3 iterations, then after 4 iterations, then after 5 iterations, etc. The set of all points that are not in any of those open intervals, the intersection of whatever is left over, is called an invariant Cantor set. It's the set of all points that never leave the interval after any number of iterations. And it is not exactly equal to the Cantor set that people talk about when they talk about the Cantor set, which is this thing up here. Come back here. But it's analogous to it. It's similar. So overuse the word similar here. It's a similar kind of thing, I should say. How do you make the Cantor set, also called Cantor's ternary set? The reason it's called the ternary set is because it's most easily described in base 3 decimals. I should call them decimals. Base 3 arithmetic. Binary is base 2. Ternary is base 3. The Cantor set that people typically think of, this one, is best described with base 3 in arithmetic, representing numbers in base 3. You take the entire unit interval from 0 to 1. You take out the middle third from 1/3 to 2/3. Then you take out the middle third of each piece that's left. This is from 1/9 to 2/9. This would be from 7/9 to 8/9. Then you take out the middle third of each of those 4 pieces that are left, getting 4 new intervals that are taken out. Then you take out the middle third of each of those, getting 8 new intervals taken out. 1, 2, 3, 4, 5, 6, 7, 8, etc. The intersection of all the darker pieces, as you continue its process forever, is called the Cantor set, or the Cantor ternary set. It's got lots of interesting properties. For example, it's closed, since it's an intersection of closed sets. It's also an example of something called a self-similar fractal. If you zoom in on any piece of the Cantor set, sort of think of this as your best approximation to the Cantor set down here. You zoom in on any piece of it, like this piece of it, it's going to look just like the entire original set does. It's similar to itself when you scale it down by factors that are powers of 3. This subset right there, for example, is similar to the whole. This subset right here is similar to the whole, etc. You can keep going. It's actually an uncountable set, which seems a little odd because it seems like it would be very sparse, like most points would not be in the Cantor set. Thinking of this last one as your best approximation of it. And that, in a certain sense, is true. The length of what's not in the Cantor set, or the measure is a better word to use, is actually 1, the entire same length of the interval. So in terms of measure, length, the Cantor set is small. However, one amazing fact about it is that it is uncountable. This could be another Foundations of Math project, by the way, is looking into that and proving all the properties about the Cantor set or other fractals. I do give some explanation here about some of the stuff here. You can look at it. Essentially, since the Cantor set is best represented in ternary form with digits that are either 0s or 2s, what I say there, ultimately somewhere in here, I've got some examples. That can lead to a proof that it's uncountable by Cantor's diagonalization argument, actually, that we talked about back in chapter 1. Does have 0 measure. Its length must be 0 because the length of the complement is 1, because the length of the complement can be thought of as this infinite series. Because these are the lengths of the things that we take out. First we take out the middle third, it has length 1/3, then we take out 2 middle thirds of what remains that each have length 1/9, so I get a 2/9, etc. This summation represents the total length of all the intervals that we take out, and it adds to 1. It's geometric. Anyway, it's a sparse set, but still uncountable. It's got lots of interesting properties. And ultimately what I'm trying to say is that with the logistic map, like I drew on the board there, has a set of points that stay in the interval for all time, for all iterations. And that set of points is a Cantor set. It can be made in a similar kind of way, by taking out not middle thirds, but middle pieces of intervals that remain. That set of points never leaves the interval from 0 to 1 under iteration. The points in that set get mapped to each other under the logistic map. And it's the properties of iteration of the logistic map on that set that can be modeled by the symbol space and the shift map. And the conjugacy that I hinted at the other day, which is a function from this thing called the Invariant Cantor set, which is at the capital lambda. That's the Invariant Cantor set. Here's your symbol space, the set of all sequences of zeros and ones. You can define a function called a topological conjugacy that's one-to-one and onto, is continuous, and has continuous inverse with respect to the metric space topology. And also has the property that these equations are true. And because of those equations being true, in a nutshell, without explaining why here in the details, iteration of the shift map on sigma sub 2, the symbol space, the sequence space, corresponds exactly to iteration of the logistic map on the invariant Cantor set. They match up exactly. You can prove properties about the shift map on the symbol space, for example, like that it's got a periodic orbit, or that periodic orbits are dense. The same property is going to be true for the logistic map on the invariant Cantor set. Without explaining why, okay? We don't have time for that. It could be a foundations of math project to look into that more deeply and prove that kind of stuff, if that kind of thing interests you. It is similar, I will say, to the idea of similar matrices, again, to overuse the word similar. From linear algebra, you get a similar kind of equation relating to matrices A and D. That you might hopefully remember that from linear algebra. If A and D are related by that kind of equation, they're going to have similar properties. They're going to have the same eigenvalues, for example. Essentially, A and D are modeling the same linear transformation, just with different coordinate systems. Okay. So it is a pretty similar idea. A topological conjugacy is analogous to this idea from linear algebra. I do have a hint at a proof here, I think. Yeah, this thing sort of is an outline of the proof that periodic points get mapped to each other. But again, if this interests you, you can delve into this more deeply for your foundations of math project. And I can help you if you want help with it. All right, let's do our more general review. So like I said, you're going to have the closed book portion of the exam, no book, no notes, which will consist of definitions and theorem statements from Chapter 8, possibly true-false as well, I'm not sure, related to Chapter 8. And then you've got your, just a second here, open book, open notes portion, where you can use your book, you can use your notes, and your calculator, by the way, bring your calculator. So I might have you do some iteration in your calculator. I'll try to remind you over the weekend. Although I'd recommend maybe writing a lot of stuff on a piece of paper, that's a quick, handy reference, so you're not spending too much time paging through the book. Question?
As far as the theorems, since there are so many that are not really like labeled, other than theorem, whatever number.
I'll talk about it as we go.
Okay. And then the calculator iterations, is there some function on the calculator, or is that just going to have to be inputted?
Yeah, there is a quick way to do it in the calculator, actually. You can use the A and S key. Like, for example, if you want to iterate, to think a simple example, f of x equals 2x, plug in your seed, like 5, hit enter, then go 2 times ants, hit enter to get 10, and then keep hitting ants over and over and over again. You'll get then 20, then 40, then 80. This example, you keep doubling. Okay, if you want me to show you, I can. Annie, you had a question?
Yeah, I was just gonna ask for the, chapter 8 section with the definitions in here, will there be problems to work out as well, or will it just?
There could be in the open book portion of proof of two or calculation.
But the
like
closed book
iteration.
part is just gonna be writing out theorems and definitions?
Definitions and theorem statements and possibly a truth and true false.
And that's only from chapter 8?
Only from chapter 8, yeah. So let's summarize chapter 8 as the main bulk of what we do here in our review. I'm sort of going to label these section by section, although in each case I'm lumping together section 8.5 with the other sections, 8.1, 8.2, and 8.3. We basically skipped 8.4, though I suggested reading a few pages in it. Definitions, what's an interior point, what's a limit point, what's an open set, what's a closed set? Should be able to do those on the real line. If I ask you to do them just on the real line using intervals, you should be able to do that in a metric space. You got a metric space X.